A very common question, which most of the physics students must be aware of. Like, in which preferential order do you study mathematical physics? Is it like you cover the whole maths topics which you are gonna encounter first, then move on to the physics of it, or is it like you start the textbook, whatever mathematical concepts whatever mathematical concept the author throws at you, you just cover it simultaneously with the mathematical physics book. So, for example, like if one wishes to start from scratch studying general relativity, so it is always suggested that he should first finish the differential geometry, multivariable calculus, and some part of linear algebra, some expertise of linear algebra, and then start with the textbook. Or is it the other way around? Like you start with the textbook altogether without any hint of doubts here and there, and then tackle the maths which comes along. So which one is more beneficial in the long run? So yeah, I would like to ask Chintan on it. What you have to add on this, Chintan? Over to you.
Yeah, so there are two kinds of mathematical preliminaries. Like one are the very basics one which you have mentioned, like linear algebra, multivariable calculus, ODPD, which I think you should do first without doing actually any of the physics topics like quantum mechanics or quantum field theory. Anything requires these topics. So maybe you should pick some standard book, as I said already. Afkan and Weber is the perfect book for these topics. And other kind of preliminaries are these differential geometry kind of things. So they are like very specifics, which are not mentioned in any of these. Even some graduate mathematics textbooks, mathematical physics textbooks don't have differential geometry. There are dedicated differential geometry books on this. So if you try to follow that definite differential geometry books, I think you will be like in trouble, because they are very deep and they might take off a lot of your time. But if you are following a textbook, good textbook like Carroll's textbook is very good for general relativity. So what he does is he explains all the differential geometry concepts, like what is metric, what is curvature, and so on in initial first 3 chapters. So that will be enough for whatever is given in the textbook. And there are also some extra concepts in the appendix that you can follow. So it's the second way, I think, which I would prefer for such cases like GR, like physics with maths. But if you are talking about the concepts which are like linear algebra or multi-calculus variable, then the first approach is, I think, more like you should be familiar with these basic mathematical concepts, which will be useful in almost every topic.
Yeah, thank you, Chintan. I would like to hand over the podium to Vishal. Vishal, I would like to add something to this.
Yeah, I would like to add this. So it's the same thing. Like you cannot give a lot of time to studying maths first. Like if you want to understand canonical quantization for quantum mechanics, and if you want to study it from a mathematics perspective, it will take you 3 courses in mathematics first to do in order to even begin to understand what is the operator. And then you start quantum mechanics, then that is the time when you start the first page of Griffith. So it's going to take a really long time. So for an undergrad level, definitely physics, math, and as Chintan said, everything. So, but when you're at a grad level and you're solving a new problem, and then you have to learn about whether the problem is ill-posed, whether it has some problem with initial values and things of that sort. At that time, definitely, at that level, you should get to know the math. So you should not skip it at that level. So at a much later stage, definitely you need to learn the math. Like I have a paper in hand and which shows it. I can share it in the link if is required. Which shows a problem in general relativity, which had to be solved through learning more mathematics. I think I'll share that in the chat box now.
That would be great. So over to Bhavya. Would you like to? You are quite interested in mathematical physics. So what is the way that you choose?
So again, this question depends on so it depends on person to person. Like if you are more inclined toward understanding physics, and math is just a tool which is being used to understand physics, and what you can do is you can have some physically motivating example. You study that math, you study the math, then you go back to physics, and then you can do this oscillation and learn in this kind of fashion. That's perfectly fine. But if you are a kind of person who also like to learn math in its own sake, then I would always suggest that first learn mathematics and get confidence over the mathematics. It will surely provide you with a toolkit in which you can like there are examples in which when you have a nice rigorous mathematics background under your belt, you can argue many physically interesting results also. For example, there is this interesting example of particle statistics. So commonly there are known that there are only fermions and bosons, right? And we have been taught that there are fermions and bosons. But if someone has some background in topology, then he or she may argue that in 2 dimensions you can have non-trivial particle statistics other than fermions and bosons. You can have in principle infinite particle statistics governed by some continuous phase, which is precisely called as anyons. So this simple physical insight is coming from purely mathematical, to be precise, topological arguments, right? Now, what if you have learned math precisely in the rigorous format? What you have is that you leave these kind of pockets where you can find some physically interesting results using these pockets, right? If you have learned topology, you can really derive these kind of exotic spin statistics relations and so on. So I think like if you are comfortable with doing math first and then tackling physics afterwards, and you have, even if you don't have much time, you surely should devote your effort in learning the math before physics, and then I think you would be much more comfortable with physics and can have these kind of small pockets where you can obviously derive some interesting physical results. But if you are not comfortable, then obviously that route is also very much possible, that you go back and forth and you tend to develop this kind of route.
Yeah,
Person to
yeah.
person.
Yeah, totally. As all of these questions are subjective, so there couldn't be any absolute answers. And
I would like to add a small point. So, like last year, so the Nobel Prize was won by Penrose, and he's actually a mathematician himself. So, and then he started doing black holes and everything. So, he was a mathematician turned physics.
so we must learn to realize that what tools are necessary and what tools are would be helpful in overcoming the war in which we are heading towards. So, with that thing, I would like to move on to our next question, which is the 6th question in our list, and it asks like what minimum of a mathematical physics background is supposed to have for a student entering in MSc Physics. Like we have a pretty detailed syllabus of JAM and JEST, which covers most of the beginner things. But I think this is not exhaustive enough. So, Bhavya, as you have mostly read mathematical physics on your own, so would you like to add some topics which are left in the JEST syllabus altogether? Over to you, Bhavya.
Yeah. Like according to me, what when I learned through textbooks, which are so-called graduate level textbooks, but there are some mathematics which can be learned in undergrad, and it's more of like diagrammatic approaches and so on. One of them is algebraic topology, I think. So algebraic topology has this kind of nature, and even in general topology has this nature in which you tend to draw a lot of diagrams, and you can derive very insightful results without going into much rigor. So I think that one topic is surely can be picked up by undergrad, and you can surely like read up on like homotopy or homology theories, which, as I said, gets you to derive these spin statistics theorems and so on. So that surely is one subject which an undergrad can pick up without much mathematical prerequisite, because you can obviously derive homotopy or homology groups for simpler spaces just diagrammatically. So that one topic is there. Second topic is what I think is a personal suggestion, is differential geometry. And why I'm saying that this can be picked up by an undergrad, because we have this awesome series lectures by Schuller. So Frederick Schuller series on the Virus Institute of Winter School on Gravity and Light. Those lectures are the appropriate has the appropriate level which an undergrad can study, and he can also study how to appreciate pure math and physics. Because when I learned, I was in my second year, and I was not like that much, didn't have that much background in physics. Okay, and I was already in my was majoring in computer science. So even a student like me can pick up from those lectures. So I think students who are already in physics programs can surely benefit much more than. And those lectures are like, those lecture teaches you that pure mathematics, if you introduce it slowly, steadily, and intuitively, you can induce rigor even at undergrad level. You don't need any graduate level maturity to appreciate rigor. You can do that even at an undergrad level. So I think differential geometry can also be added up into that list because of the Schiller's lecture. Then after that, group theory can also be added in the list, because group theory also does not require much of rigor. You have some axioms, and then you have a lot of examples from your elementary physics which you can use to motivate why groups are required in physics. And so those examples can be read up in undergrad courses, and then from scratch, how do you build representation theory, that can be left up to graduate level courses. But yeah, in undergrad, you can learn a lot of examples of groups. So that again can be tackled in undergrad. And then some analysis can also be added. Some analysis won't be like too important in undergrad, but I think in graduate physics, if you want to do some kind of pure math, it will serve you as a nice prerequisite, and you will have a much more experience in analysis than people who start in a grad school itself. So some analysis like set theoretic notions like continuity, compactness, connectedness, topological spaces, metric spaces, and so on. A basic definition. It does not require any rigor. There are just definitions, and from those definitions, you have some theorems, lemmas, and so on. You can cover that in undergrad. But yeah, this kind of topic can be left if you don't have much time. But yeah, first 3-4 differential geometry, algebraic topology, that surely undergrad can tackle.
Yeah, that was pretty something to note about, because I think I should have started with a pen and a paper. But anyways,
The chat. Yeah. Okay.
yeah. So actually, I have read a very good article by Gerard T. Hooft, and he has prepared a comprehensive list on the theoretical aspects of physics and what one should have learned as a beginner. So I am posting the link in the chat box. So guys, please do check that. And thank you, Bhavya. That was really very appreciable to share such sort of knowledge. And moving on to our next question, which is like, what steps do you take to remember things? I think this is a pretty common question, which most of us monkey baboons would find relatable to. Like we come across many proofs, derivations, and end results, and our Indian exams are mostly hungry about what you learn as an end result rather than the derivations in most of the exams. Not an exhaustive thing to say, but yeah, in order to develop a substantial understanding of physics in the long run, do we need to remember things? Like, do we need to remember the proofs and derivations as well as the end results? So one basic example of this would be like superposition of a translation and rotation. Like just suppose like we are encountering a problem of both motion, like translatory and rotatory, and we used to solve it by taking into account first the translation motion and then the rotation motion. But there's a very beautiful proof behind this, why this superposition works, and why isn't there something else rather than this. So most of us don't give much attention to it. And is such kinds of are such kind of derivations necessary in the long run or not? Or is it just the things which you get as an end result, the very important thing? So over to Vishal.
So, my personal opinion over here is that it is good to remember the concepts and the assumptions made to get the end results rather than remembering the derivations itself. So, the assumptions are very important, so are the end results. And it's good to memorize the basics, not all the stuff. So, whatever are the basics, that needs to be remembered. And definitely over a long term, you are going to forget something or another, and you have to Google. So that is unavoidable. So most of the things you are going to forget if you don't use it for a couple of years. So in the end, you are going to Google. And this example of superposition of this translation and rotation, I think that such proofs need to be done about once or twice, most probably once. But after that, you are just going to remember this thing. And if you are curious about it, you can go for it once and look at it. But you're never going to remember the proof. Like certainly, if I don't remember it right now.
Yeah.
That's what I would want to say for this.
Okay. So Chintan, would you like to add something?
Yeah, so I partially agree with Vishal that most of the things you don't remember, even the end results or proofs. So if you think that you want to remember this certain some derivation or something, then maybe you should write the derivation in your own terms. What are the key ingredients of the derivations? Like there are certain steps which if you remember, then you can follow all the derivation by some mathematical algebra. So if you think that certain derivation you need for some other application or something, maybe you should do this, like write it in your own words and try to derive it, try to do the mathematical algebra once at least, and then it may help to remember in future.
Very nicely put. Actually, we require it mostly in the interviews because we are asked to derive things right at there. So it is necessary to remember at least 2 or 3 steps which could lead us to the end result. So I would also like to ask Bhavya if you would like to add something to this.
No, I think mostly Chintan and Vishal has covered the answer. But one thing I like to add is that they said that what things you don't have to remember, but you do have to remember where you can look at the details or the derivations, right? So you forget the details. You remember the big story, big picture. What are the puzzles? What are the assumptions? You remember that. And you surely can derive these things, but there are some details which need some kind of trick or that kind of thing. So you do remember what all sources you can look up to get those details. And so once you are done with that, then that's how I think research is also done. Like you don't remember everything, but you do remember what all literature you can see to get up those details if you require.
Okay, thank you, Bhavya. As a postscript to this question, I would also like to add here, this is a very common thing which many aspirants ask. Like while preparing notes for exam is altogether a different thing. But preparing notes while you are reading a textbook, and obviously you would not like to go through the textbook all together, all at once when you need it. So what should be done while preparing notes when you are not preparing for any exam? What should be the key points which you should keep in mind while making notes for non-exam oriented kind of perception? Anyone, if you would like to ask, like Soumya?
Hello.
Yes.
Yeah. So the question is interesting that when you read something which is not required for some exam or some other purposes. So what I would like to add in this point that the remembering of the proof. So there are 2 kind of proofs, that some proofs looks very trivial to you and some proof does not look trivial to you. So when some proofs look trivial to you, so you then have some argument. You have some argument in mind that why this looks trivial to you. So write down those arguments. Right. Maybe the actual steps are very different from your arguments, but if you write down your arguments, then you will remember that why this proof looks so trivial to you. And the next thing about when some proof is not trivial, you go through some of the steps which are may refer some of the theorems which you never heard. Right. So in that case, it's very difficult to remember all the proofs. But if you have some suppose someone asks you about the proof, you write down the main steps that to go through go through the proof. Right. You write down the main step 1, 2, 3, 4. Maybe step 2 and 3 is very different. But you have to write down this thing. And for your question, that if you write something which is not for exam purposes, so just what I do, I go with the examples. See, what every time I am mentioning that if you are if you are learning something, make analogy with some examples. You may forget the actual thing, but you will never forget the example. Right. So I remember sometime while I'm explaining limit, that mathematical limit to someone. So the guy was 11 or 12. They asked me why I am doing that limit x tends to 0 or x tends to infinity. What is the physical interpretation of it? Right. So then I told them the story about that Zeno's paradox. You know, everyone may be familiar of the Zeno's paradox. That a moving person, the paradox is that a moving person can never overcome another moving person. See, so these are some physical examples which are based on the mathematical concepts. Right. So if you write down those examples when you are reading maybe some 1 month, 2 months, 1 year later, so this example will motivate to remember those things.
Yeah. Okay. Thank you, Swami. It was very nicely put. Like we make mnemonics for while preparing for exams. So instead of making some song or something of that sort, make real life examples which are associated with the derivations or proofs which you are trying to remember. Yeah. So that would help at least to 2 or 3 steps of the derivation. Then you could fly along with that. So moving on to our next question, which is 8th number. It is just some. I would like to ask basically what tips regarding self-study would you give to someone who wishes to pursue experimental physics? As an undergrad, I have talked to many undergrads of my age, and this is a very similar thing among us all, that we are not much exposed to the experimental side of the physics. As the curriculum suggests and as the present state of Indian education system is, it is the least exposed side of physics. So I would like to ask Ganesh, what would you suggest to someone who is really interested in experimental physics and wants to try their hands on? Over to you, Ganesh.
Yeah. So my answer is very trivial. Is that if you, for example, you are a BTech student who is trying to pursue physics, then you don't know that you want to do theoretical or experimental, and because you are unsure of what you like, you should always look for an institution that has researchers who are doing both experimental physics and theoretical physics. That's what I did. I didn't know what I wanted to do because I didn't have any exposure when I was doing BTech. So that's why I went out of my way to choose an institution like University of Hyderabad, where there were both people who are doing theoretical research and experimental research, so that I can have exposure on both the things. Experimental physics is something that when I went experimental physics, I knew that first of all I was rubbish at it, and second thing, I don't like it. Only I had to go and try, and then I knew that this is not for me. And that I had to try. I mean, I did a winter vacation, and there I did a project on lasers, and I didn't like it. Then I did my MSc thesis in theory. I liked it. So that is something that you have to try, and then only you will know. And experimental, this is again, what do you call, a regionalist answer. If you are in places like Mumbai, Pune, or Bangalore, there are institutions that are spread over who will do experimental physics. You can write to one of the profs, say that, yeah, I will not bother you, I will not do anything, I'll just talk to your PhD student, I'll spend 15 days in your lab, will you let me do it? That's a reasonable request. It's not like asking, I'll do an internship, you write a paper with me. If you just want exposure, you can walk into any lab and you can do so. But if you are in places where there is no institution that does experimental physics, that is very hard to do so. Then again, there is a very special branch that is like, for example, people who do the people who work for CERN. Many of them are experimental researchers. They do data analysis on a daily basis, and then they need the intuition that an experimental physicist has. That doesn't require anything. You need a computer and an access to the CERN data bank. So if you are into that kind of stuff, you're fine. Then write to a researcher. They are mostly, almost all of the services I've met are very, very nice. They'll give you access and you can work on that stuff. So the answer is, either you walk into an institution and try out doing experiments, and when you are choosing MSc, you choose an institution that has good experimental facilities, or try to do these long experiments, like, so for example, people who work in astrophysics, right? The observational astronomy, they require, you need to do computation. That is still experiment, right? So that stuff you can try out, or you do the same with certain things, or the observatory in Antarctica, the neutrino thing. That stuff, most of the researchers, some of them are staying in Antarctica, but most of them are outside in other 6 continents, right? So they are doing stuff on their own using a computer. So that kind of thing you can try out if you want to do experiment. Other than that, there is no other way there is no better way of understanding doing experiment than actually doing an experiment. So if you have to travel and go to an institution that will do experiments. That is my suggestion.
Yeah, thank you, Ganesh. It's like what perturbation theory suggests. Just spread out and find. That's the basic thing. So yeah, I would also like to ask Soumya if you would like to add something to this.
Yeah, so most of the thing is already covered by Ganesh, but I want to cover some another thing, that if you are going into some experimental physics, you should be very much athletic, right? So I have visited some of the labs, and the people, they told me they spend 8 hours, 10 hours, 12 hours in the lab, and with a temperature, say 15 degree, 10 degree, right? So if you are not comfortable with that, means lamely speaking, if you are not comfortable with a test match, which start at 9 a.m. and goes up to 5 p.m., right? And all day you are just doing the fielding. So if you are not comfortable with this kind of thing, don't go to the experimental background. Rather than you choose the second option, what Goyana was telling, that the data analysis part. You are still part of the experiment. See, when an experimental paper comes, you will see 10 to 20 names. 10 to 20 names in the paper. So there are maybe 50% of the people are doing the real experiment, and in the back end, the data analysis thing, they are done by the 50% of the student authors, right? So try to choose which one you are trying to go. As Ganesh said, that if you are going to the real experimental one, you should be very much athletic, to my opinion. Right? As he said that you have to go Antarctica, you have to be that an adventurous kind of guy, and you have to be physically and mentally fit. So that's what I'm telling the point. Yeah.
Okay, that's brutal honesty, to be very honest. But okay, moving on to Vishal, would you like to add something?
Actually, most of the points are already covered. All the things, almost everything I wrote down. So just one point, a couple of points was remaining is that, like as engineers, like it would be like nice if they could get into an experimental physics, because all the knowledge which they gain in say material science or mechanical or electronics, they'll actually be using that in a physical and understanding of physical system. So if they can understand modern physics, which I think most probably will all be understood by the time you are prepared with the exams, you have the physical motivation. Now all the knowledge which you gain for the 4 years can be applied directly now. And it will be, and few of the students, few of my friends who are working in experimental physics, who did engineering, they kind of regret, "Arey, engineering thoda aur acha kar leta, tabhi maza nahi aa raha tha." Now I'm able to understand why it's so. If I had studied that, I would have understood it much more better now. And when they go back to the textbooks, because they have the motivation to study, so it comes back to Ganesh's point of motivation, the problem. Now all the things which you found it too boring without a motivation will be becoming very, very interesting. Now I'm understanding this is I need to learn so that I can crack this problem now. So as engineers, since that is most of the things which you do, so experimental physics would be very, very easy coming for you rather than theory, because you'll have to pick up mathematics on the basics and everything. But engineering, yeah. And another second point is that you can, of course, visit the websites of CERN, ISQ, Bell, Fermilab, and everything. So you'll have some basic idea as to what they are doing. And there are very nice pages which these experimental labs have, which are for people who don't have any idea. So, of course, they have got research papers, but they also keep put in effort so that any person who is interested in physics can understand. So going through those websites will be helpful. Yeah, those are the only 2 points which I wanted to say.
Yeah, thank you.
I would like to. I'd like to add one point. I don't know if it's mentioned already or not. Is that while interacting with some of my friends who are in experimental physics, and I think Vishal will also agree that data analysis and coding has become very important nowadays in experimental physics. Like the hardcore experimental physics where you design the experiment and all is already done. Like those experiments are designed way before. So I think one should give importance to coding and some techniques like Monte Carlo techniques or something that can be done at undergraduate level, I think. So that are like very important techniques if you are going into experimental physics.
Yeah, thank you, Chintan. So in a nutshell, if I wanna address to all the Nobel seekers who want to get into theoretical physics just by the name of getting a Nobel. It's not necessary to earn a Nobel being an Einstein. It's also as important to earn a Nobel like this year Andrea Ghez did. So there's both sides to it. Just perturb around and find it. That's the basic thing, which would be the cause to queer your curiosity. So that would be all for this question. I guess we would move on to the next question, which is ninth one. There's one more left, so don't go anywhere. We would be ending this pretty soon. And the ninth one is like how to get updated on the latest physics and science results in order to form a perspective on what you should want to do research in. Like how could you correlate your interests and the findings of present era to collide on the same path. That is the concept behind this question. So I would like to ask Vishal about this, as he has done his research in this field. So yeah, Vishal.
No, I was just looking for some articles. It's not like research or something. So okay. So most of the textbooks which you're reading are, except for the quantum field theory, like the extremely recent results, most of the textbooks are at least 100 years old data is there, and 100-year-old equations is there. So it's very much important that you actually get to know what is happening right now, because research is based on what is happening right now, and you're going to build on that rather than having a 100-year gap in between. So that's why it becomes important that you become updated with physics, which is happening not only in India but in the overall place. And nowadays there's a lot of interdisciplinary results, so that's why it's physics and science together. So just don't be in just a very small area. Of course, you're going to do research over there, but don't be confined to that. So at the interface, there's a lot of fun stuff happening. So I'll post a few pages which you can look for. Like there is a Physics World and Physics Today, and in Nature, which everyone knows about. So it has got its small briefings in which for general audience, it has got very one-page short articles which you can look for. So these things, I think it will be really nice if you can read and get a hang of it. Because, like as an example, I can tell you for like why you should not just confine to one thing. And if say like Higgs physics, like that was because a person was able to take an idea from superconductivity and apply it to particle physics, for example, and that is how the Higgs physics came into being. So you cannot just go into just one area, small area in itself, and say that that's the thing. And I'm also going to link an interesting article called Birds and Frogs. So birds are the people who have got a very wide angle view as to what research is going on. And frogs are like, they just know their very little pond and they know each and every centimeter of that. So actually you need to have a perspective of both, and so that's how research will progress. So I think I'll add these things in the chat, and that's all I had to say for this question. Because most of the things you have to read over this question, because I can just send the links.
Yeah, thank you, Vishal. It would be very great if you add this in the chat box. So, any other panelists would like to add something to this, or we should move on?
Yeah, I want to say something. So, I mean, I'm pretty sure everyone knows what archive is. If you are a graduate student, I would consider it a mortal sin if you don't visit that page in your own. I mean, if you are doing quantum high energy physics, you would visit archive.org HEP, or if you're doing quantum information theory at computation, the quant PH page, because the existence of that archive, that open source archive, that is followed by everyone. That is important. Okay, there are a million other things called NASA ads, or there is something else called semantic scholar, so many other things that are still this archive-based things that you put the paper for free and people will notice. The point of this is that archive is widely accepted throughout the world. Any reasonable researcher who has any sense of what he's doing, he would put his paper on archive. Okay, unless he had an extraordinary result that he's afraid of people stealing it, usually they put the paper on archive. So if you are doing research, you are a grad student and you are doing something, you should always visit that page. And at first, in the first stages, it will seem like everything is new, but once you go through this step of initial thing, you will see that words are repeating. That is the first sight of intuition that, yeah, this is a trend of research people are doing. So, and the second thing is, when you are following results, the most important thing when you are doing research, you should always see that you are not some freak sitting in a corner and doing something. Because that will first of all will not give you any confidence that whether this is true, and second thing, whether this is relevant or not. So when you are doing research, if you see a paper that is related to you, it will give you confidence that, yeah, my work is reasonable. I mean, this is relatable and people will read the work when I post it. So always visit archive. It will just post from Monday to Friday, and you will see so many nice things. Just the existence of this is very, very precious to this the generation of students, that researchers that are happening after 1998. Okay, that came into existence in 98. Before that, just imagine, S.N. Bose has written the paper on this statistics, his so-called S.N. Bosonic statistics. He had to from Dhaka University, where he was doing it. He had to send a post to Einstein. Einstein didn't receive it. He was a fancy scientist, so he had a PA. His PA saw it, and after a week, she gave it to Einstein. There was almost 3 months gap where Einstein didn't even see the paper. Today, if you post a paper, most of the world will see it if it's relevant for them. So even that is a 50 story. Let's talk about Amitabh Rai Chaudhuri. That guy wrote the torsion equation, and none of the Indian scientists knew about it. Some German scientists, just because Amitabh went and presented there, they found that, yeah, this is something new. I mean, he found an actual solution for Einstein's equation in a much general setting than what Schwarzschild has written. You understand? So the exposure through archive is huge. So you should never miss out on this resource. As a grad student, it is very, very important for you to visit archive every single day. that is a source of inspiration for ideas every single day. That I find that whenever I go there, I'll write down some stuff that possibly my future project will include this. So archive is an extraordinary resource, and you should all visit it.
So what have you got here while opening the Pandora's box? We got a lecture on archive. So I would definitely, I'm going to visit it just after this meet ends. And that is a very good thing to say. Like apart from scrolling here and there and all the magazines and all the pseudoscience or pop science articles over the internet, we can surf these sites. And surely we will get something big in return if you are curious enough about all the topics which you come across for the first time. So Chintan.
So I don't think if everyone, I think mostly everyone will be familiar with this, but ICTS has this ICTS talks if one is interested in mathematical physics or string theory. Like if you just subscribe to their channel, you will be knowing the cutting edge research what is happening in these fields.
Yeah, ICTS regularly post such talks on their YouTube channel, right? ICTS
great researchers in like fields such like for example Juan Maldacena, if you know, in black hole physics. So he also gives regular talks on this, and you will get to know the current edge research what is happening in these talks. So
nerds, get beyond the beyond the word of your books and go surf the internet. That's the nutshell answer of this. And moving to the last question.